Hello, welcome back. If you're watching this and you haven't seen episode 1 yet, where I explain what the heck we're talking about, please go back, follow the links, and do that first, or else not much of this is going to make a whole lot of sense. We're going to try together in Java and writing the game of life, practice out discovery testing. It's a new concept for a lot of folks, and a lot of folks have dabbled in this without getting like somebody to pair with. So I'm going to just walk you through it, mostly how I'd really do it, except with a lot more explaining along the way. We're going to start with something I wouldn't normally do, but sometimes I do when I'm facing a hard problem, which is kind of go to the whiteboard together and design from the top down a little bit of what we think, only one layer at a time, what we think that topmost layer of our system really needs to do. Normally, I use the code itself, the test itself, as the sounding board and iterate on the test doubles and their APIs and the values that get passed between them. But I think it can be much more easily visualized as a tree, and most code and files and class structures and stuff inhibit that visualization. So we're going to first just talk about what we're doing in visual terms, and then I'm going to switch over to the code and do the same thing there. All right, so we know that we're building this thing called Game of Life, and that it simulates this infinite world full of cells in a grid-like system. And whenever I hear that question, I try to think how would I solve this in relatively ideal terms. That infinite grid aspect always drives me nuts, because obviously if you can just say the grid is 81 by 81 or whatever, you can just build a little 2D array and plop things in, and then you're done in no time. And so I really tried this last time when I was thinking about the screencast, I really tried to noodle on how would I approach this if it was truly infinite insofar as limited only by our time to compute what's out there. So using one single seed, kind of just discover the periphery as wide as we can for each round, based on some kind of arbitrary other limit, as opposed to the bounds of a 2D array, and maybe the number of milliseconds that we're willing to yield for each subsequent generation of the test, of the simulation. So pretend at the top that we have some object called simulates Conway, and that's our entry point. And if we try to imagine the code that we wish we had to break that big problem down, not just generating the seed world and figuring out how to do that stuff I just mentioned about timing, the number of iterations to do, not just how to lay out the grid, find the neighbors for a cell, break all those rules. Really easy for me to get tied up in the details. If at a very high level I ask, what are the relatively, smaller things that simulates Conway might depend on to get its job done, I might think, the first thing that we need is something that generates that seed world for us. And that implies just that we need the value object of a world somewhere. So that's going to be the first thing to shake out of this. When simulates Conway calls generate seed world, it's probably going to get something back. We can call it a world for what we care. It's going to have nothing on it at first. It's just a marker class to indicate this is a value that will matter to us, and it's going to pass through the system. Second thing we need is something that is able to replace the world on each generation. So given some existing world and a time limit, I don't know what it is, a millisecond, a second, 10 seconds, a minute. Keep searching the grid as far and wide as you can go, and for each cell that you discover in the grid, then calculate based on the neighbors of that cell whether that cell lives or dies, and then return back a new world with the population figured out. I don't know, sounds crazy. Let's just cap it at it takes in a world, returns us a new world. And then finally, we need something that can output this world to the user. In this case, we're not thinking too hard about, is it a fancy UI, like a graphical output, or is it just going to dump stuff to terminal? All I know is that for each iteration of the simulation that we want to run, we should probably plan on calling something that can output it. And then the implementation of that output we can defer to later with this approach. We'll still be able to get our passing test at the top level, and maybe later on, maybe we start with CLI, terminal output, but then we add some configuration to let you spin up, a full-blown GUI. So, given all that, that's the basic plumbing that I have in mind. Given the constraints that I've placed on us extrinsically, that means that there's a couple parameters that we need to pass into simulates Conway. For example, like I've defined it as a discrete number of generations that we're going to simulate. Obviously, if we just let it run forever on a never-ending while loop, that would work too. But I'm placing this constraint on us for simplicity. And additionally, the other one, the time limit per generation, is maybe a novel idea, so we should pass that in as if it's a configuration property. Then when we think of like how the data flows from that point forward, Simulates Conway should be able to call the generate seed world without necessarily passing anything along to it, because it's mostly going to be random. There's not really any configuration of a world, it just exists. And generate seed world, that whatever we get back from there, we probably want to relatively immediately output it, since that's a done generation. That's our first generation that's done. But pretty quickly after that, for however many number of generations, we might want to loop over that number and replace the world. So for each generation, we'll call this thing maybe replaces world, giving that seed world initially, but then feeding into itself every subsequent world for each generation, calling into itself. And then, of course, we want to output each of those generations as well, so it'll call output world. So at a high level, in this first episode together, I guess, all we're going to do is the test of that very top layer. And we're not going to worry about how replaces world works. All we're going to do is write a test of the top level that specifies all of the interactions that we need in order to focus on just one of the three problems that will remain after this test passes. So after this test passes, my mindset is, okay, now I get to choose generate seed world and work on that stuff, or outputs world and work on that stuff, or the thing that replaces the world and work on that stuff. And my rule of thumb, whenever I have the freedom, is to always choose the highest risk thing to do next. And I know that generating the seed world is not going to be tough, and I know outputting the world is not going to be that interesting, so I'm going to probably dive into that middle layer. And so that's probably what we'll dive into next. So, given that, keep in mind that, we're pushing away, we're deferring all the other work that happens down at the bottom layers of the tree. There might be 4 more layers for all I know. Obviously, you don't want to keep these trees too high. You don't have too many layers in a system. But there's a lot of work that's going to happen later, and I just have to keep flushing from my mind all that minutia, which is challenging for me to do. I get really hung up on that. All right, demo. So I have installed Eclipse, gotten my favorite settings in place, started a project that is currently empty. I'm going to show you what I put there first and make a quick git commit while I'm at it. So let's get out of Keynote. I'm going to pop open into Terminal and create a git repo for ourselves. So I think I've dropped everything in CD code Eclipse. Probably the thing called Game of Life. All right. Whenever I use git, I just git add everything and then commit it without looking at what it is. That's not a very good practice, but okay. Initial commit. There's probably some stuff I wish I could ignore there. Yep, like that whole first half and second half of stuff. Crap. Alright, so I'm just going to kill that real quick. Touch git ignore. This is the only time we're going to be using Vim, because the rest of the time we're going to be in Eclipse. So I want to ignore target. Blah. Target, settings, class path, project. Try again. Okay, cool. These are the only 2 files that should be tracked at this point. We'll take a look at the POM in a second. So git add star. By the way, whenever you have trouble with git, just remove the .git directory. Everything will be fine. Just kidding. Please don't do that. Alright. Initial commit is always the best message for your first commit. Alright, sweet. We got something in Git. Killed Keynote here. Get out of here. Enjoy my nice wallpaper of a cheetah eating something. And head over into Eclipse. So here we are. This is Eclipse IDE. Stuff on the left shows off my projects. Stuff on the bottom shows off an infinite number of tabs of things that Eclipse can do. We're going to focus almost entirely on the JUnit tab and the Project Explorer, and then ultimately our code, which we'll try to full screen as much as possible, get the IDE out of our way. But Here you can see I've got a couple packages in mind. I'm going to just drop everything in com.testdouble.gameoflife. And always trying to start with the class first. Let's start with the test first. Let's start with a test class. I don't mind hewing pretty closely to what we wrote in our little design session. Simulates Conway singular. It's a singular thing. And this is the test, so simulates Conway test. Why not? Now, in Java, I don't really like having to write the boilerplate of importing everything over and over again. It's too error prone, takes too much time. I'm always looking to try to reduce the amount of friction needed to create a new unit, to create a new test. So I'm going to kill this, and I've saved a couple snippets. There's really two types of tests. Those with test doubles that are designed to drive out and shake out the design of your units, like these are the dependencies you're going to need. And then there's traditional tests, which should not have test doubles, that are trying to ensure that we're building a working thing that has some logic in it. So this is the former. So I'm going to use my test Mockito shortcut here. And it's got a lot of junk at the top that I won't explain too much. Just to say, we're using JUnit for the basic test runner. We're using Hamcrest for some assertion matchers. We're using Mockito as our test double library. Mockito is an excellent test double library that's inspired lots of really good ones and is a great fit for discovery testing. In fact, if you use my testdouble.js library that I referenced earlier, even if you take what we do here and only ever use it in JavaScript, testdouble.js's API is designed to mirror Mockito as closely as possible with only a couple tweaks. All right, so the way Mockito works is you can use this little annotation to say this is the thing that's under test. I always call the thing under test subject, and here I've given it the type that doesn't exist yet of the thing that's under test. So I'm going to go ahead and hit Command 1, which is going to let me autocorrect. Because of reasons, I have to tell it to go into the main source folder by default, and now I have my class. And I've got some unused imports here, but that's because we don't have any tests yet. So let's see, how do I want to start? Probably if we're thinking about the number of iterations, the number of generations we're going to do, let's start with an easy case. Let's try to just do, if we pass it in 0 iterations, what do we get? That'll force us to drive out the generating the C world and the output stuff. So the first mock that we need, and again, it uses the term mock. Technically, this is a spy, so the nomenclature is a little bit off. If we had an object called generate seed world. I like verb noun naming of my objects because the verb is what matters, and over time, if the verb stays the same and the noun generalizes, we end up with slightly cleaner designs than the other way around. If you've ever been in a Java project with a bunch of stuff called managers or processors, that's the result of inverting the verb noun stuff. All right, so as I was explaining that, created a new thing called a mock. It's going to get injected into the subject. All I did was Command 1 click, and it created that class for me so I could get rid of the red squiggly lines. The other thing I think I'm going to need right now, because I want to be able to verify something happened, I'm going to say mock outputs world. So when I think about this test, I'm thinking there's nothing that this thing that outputs the world could really return to me that would be useful at this top level of the application. So functionally, what we want this whole simulation to do is to have a side effect. Side effects have problems. They're harder to test. They're harder to assert. They can make parallelism hard. Side effects are bad. But a lot of systems that we build, at least logically have a lot of side effects. And when you have code that has side effects, the way that we test it is by verifying that we made the call at all, as opposed to verifying what it returns. And since it returns nothing, this is where you get into behavior verification kind of testing. So we're only verifying behavior here because it just so happens that the outcome that we want to see is the side effect that this thing sends a signal to output the world. So given that, let's start. Full disclosure, I've got some existing code that I've written here so that when I blank out staring at you, I'm not totally frozen. So we're going to have more than one test, so I'm going to give it a decent name. I'll say tests 1 generation, or no, 0 generations. In that case, we'll need some kind of world object to verify that this is the world that gets called. You know what? To be honest, I always break up my JUnit tests into 3 phases. I call them arrange, act, and assert. And as long as you follow this 3-phase rule and you give it a little white space between the 3 so it's obvious which phase you're in, then even though you don't have like a fancy BDD framework like a Jasmine or a Mocha or an RSpec, it can be really clear like what you're doing at each step of the test. I started typing out a world here, but technically I don't need that. I'm thinking ahead a little bit. So let's start with the assertion that we know we want. So the assertion that I know I want, so I want to be able to verify that output's world gets called. Probably give it a method named output. I like really consistent names, so the verbs, singular form will go here. All right, so output, but I know that I want to call it with, I guess the seed world, the first world here that we're going to use. That means the seed world needs to exist, so I can quick fix to create a local variable, which I know I don't want to be a general object, I want it to be a world object. And I know I'm going to probably want to set it up here in my arrange step. Alright, so quick fix that, and suddenly we've made a world. Alright. So it's surprising how many classes will shake out just as a result of using the test as a sounding board for our design. So here, I think usually we might end up wanting to discriminate what the seed world is like versus like a mutable world that the world replacing thing can change. Because the seed world is random, and that one is like more like a data structure that just gets edited or filled in over time. So there might be 2 types of world ultimately, but for now we can just use the one. And now I got another red squiggly, so I want this thing to have a method called output, which takes a world, returns nothing. You can leave that to do there, doesn't matter. Eclipse, if you're following along and using Eclipse actually has like a little to-do tracker built into it, and it'll find every to-do and fix me that you put in. So using those to-dos will actually tell you what are the layers below you that still need to be done. So it might be helpful to leave them in. All right, so we've got a world. I know that I want to have my subject, when I call it, output that world. So I know what my action step is because I just said it. So I know subject dot, I guess I'll call the method simulate, so it follows my little meme here. And this should take 2 parameters, but I don't necessarily need them yet, so I'll just skip them for now. It's going to be void for the same reasons that like the outcomes that we care about are also void. They're just side effects. And if I were to run this test right now, it's going to fail because it wanted that invocation, but it wasn't invoked, and that's because A, our code doesn't do anything, and B, even if it tried to do something, it wouldn't be able to generate these seed worlds. So I know that I'm going to have to set up that stubbing. So grab this guy. Oops, grab this guy. I'm going to tell Makito, hey, when I call this thing, when I call its generate method, and again, this is probably a no arg unless we want to start passing seeds, but for now we don't have to worry about it. Then I want you to return that seed world. Okay, so that method doesn't exist, so I'll quick fix that. It's telling me it wants to return an object. I'm going to be more specific in the type that I demand. Right now you see that the real implementation is just returning null. Because the real object is never going to get instantiated, only the testable is ever going to get instantiated, it doesn't matter what the heck is inside of any of these classes other than our subject. We can that lower ordered stuff we can get to whenever we choose. Alright, so I think I've got everything I need in the test to see that this is working. Wanted but not invoked. There's 0 invocations with this mock. Alright. Save, yep. Control J, switch over. Okay. Okay, so let's say, well, I don't have any of those 2 or 3 things that I just needed, right? So I gotta switch back now. I'm just gonna cargo copy these things. I like them to have the same names, whether they're in the tests or in the production code. That way it's just really easy for me to know where they are. Some people might name them slightly differently, but I really value that consistency so I know what it's going to be called when I'm writing the code. let's see. So the first thing I want to do is generate the seed world. So generate, neat. And since all I'm doing is outputting the world, I can just make a thing called the world. I'm going to call it the seed world so I'm really clear that this is just the first world. And then the last step here, call output and pass it the seed world. All right, hit Control R, run my tests again, and they pass. Okay, great. So we covered the first case fine. Now we're going to test a single generation. This is going to force us to do much more of the complexity. So just like classical TDD, you know, we start with a case to kind of get some of the plumbing put together when we can, and then add a more complex case next. So the thing that sits between these two in our little design is replaces world. Okay, that's going to have a red squiggly because it doesn't exist yet. So we're going to go ahead and drop that in the main source folder. And if we pass in 1 here, so I'm going to copy and paste without a single sense of shame because it's JUnit. When I call replace world, I should get some kind of second world. So that means I need some kind of second world. I guess I'll call it world 2, as if we're playing Mario or something. And when I call replaces world replace, and I pass it seed world, I should get world 2. Seems to make sense, right? Okay, so that's the stubbing I want. Of course, it's going to fail because that method doesn't exist. So quick fix returns a world, takes a world, and the world here should probably be named something like old world, I guess. Existing world. All right, so that returns world 2. Now, from a verification perspective, the only side effect that this thing has is, let me just triple check here, that I'm like outputting this thing. I could, if I wanted to be really strict, verify that the output happens in the order that these worlds are simulated in. I could, but I don't know. I don't care that much, and I know that verifying order is a little bit tricky with a lot of test double libraries, including this one. So I'm going to be fine just to say, like, you know, hey, trust that I'm not an idiot, and that I'm going to output the worlds in order. All right, so I have stubbed everything I need to so that the code can theoretically get at that world 2 if it calls replaces world correctly. And I can go ahead and verify that the second thing gets called 2. Note that I'm not doing like setup assert, setup assert. All these verifies have to happen after your act step because it's a SPY. Do all the setup, all the stubbing that you need, call the thing, and then what these verifications are doing is simply checking, was I called the way that you asked me to? So they're retrospective, and that means that they fit really well with the arrange act assert flow. That's one reason why Mockito is preferable over EasyMock or JMock in Java land. All right, so I call simulate. I realize now that the whole concept of the time limit and the number of iterations starts to matter when I say that I'm only going to do 1 generation. So I'm going to go ahead and pass that in now, otherwise this test is kind of a lie. And I'm also going to pass in some kind of time limit. I don't know if I care what that time limit is. I'm just going to say 1337 is the time limit for everything because it's not a meaningful number. And I like to pick meaningless test data when I know there isn't meaning to it. And I'll just repeat that magic number everywhere. If somebody sees 1337, they're probably going to think this is not a real important number. So that means I have to change the methods parameters, and I get defaults of I and J, which is fabulous. So we're going to call this generations and this time limit. And head back here, and that's going to create a little bit of a problem. So we're going to say 0 generations, and for this time limit, just to be consistent with the meaninglessness of 1337, we'll put that there. All right. So I think I've got everything I need. If I run this, I should see the first test continue to pass, and looking down there, 0 generations is still green. And this 1 generation says wanted these 2 invocations, but there were no interactions with that mock object. So we are good. That means that we can write a loop. All right, so for of Oh, for loops. Int equals I less than generations. Ugh. We are using Java 8, so feel free to write in if Java 8 made it any easier to iterate over a thing and retain the index. Okay, so for each of these things, let's see. I want to call replaces world. Oh, and I don't have replaces world yet, so I'll kill that. Head back over here. Whoa, I just made a split. Yikes, how did I do that? Okay. Alright, let's all pretend we didn't see anything. That's terrible. Okay, so I want this replaces world thing. Grab this. I like to put the mocks in some kind of logical order. First I generate, then I replace, then I output. Just realized my indentation is still at like 4 space width, so I can't handle it. Alright. Replaces world dot replace old world, which in this case is called seed world for the first one. This is probably not going to fly if we keep passing in the same world over and over again. Let's try to refresh my memory what I did in the first time. I think we're just going to probably keep reassigning the world as much as I hate doing that. So let's just call this world. And we'll just, every time we call replaces world, we'll reassign the world. So that's sufficiently confusing. Also note that if we do it this way, we'll have called output for all the worlds, but we'll have forgotten the first one. So if I were to run this test, I'd expect it to fail because we only should be seeing the second invocation. Wanted this actual one has different arguments. Oh, that's interesting. Maybe we're just seeing that one failure, and it doesn't see the interaction that we do want, but it did see the other one. So in that case, let's just fix it. We're going to call output 2 times. Not the most beautiful implementation ever. Uh-oh. And it failed. What did I do wrong? What happened? But was 2 times. If we reassign world. Also, we didn't call replace with what we wanted to, right? We forgot to pass it the time limit. Why is that working? Oh my. So we've messed up something. I messed up something. Shouldn't blame you. You're just my pair, although you didn't really do a lot to help. Alright, so replace thing, that needs to be passed in the time limit. We did all that work. We said it was going to be 1337. Update this. I got a feeling this is not going to actually fix my fundamental problem right now. Okay, so at least that's broken. Pass in time limit. What did I do wrong? I could try moving this in here. Oh, yeah. Whoops. So by having none of them be inside of the loop, that's a problem. Gosh. It's getting late. I'm sorry. I've been trying to think about Keynote, heads in other places. Trust me, I'm pretty good at code usually. All right, so there we go. Now we got a passing test of this thing. And what's really neat is that I implemented this entire thing the other day in a very similar fashion, and I never had to come back to this class. So how cool is it that the top level that integrates all the other stuff in our application is able to be one and done like this, just fully implemented. And even though nothing underneath it is done yet, we don't have to worry about that. So if you view programming as a task where you have to fit the entire universe in your head, we just lopped off, that whole top layer, and we can just view 3 significantly smaller problems as being discrete elements yet to be worked on. And the fact that it's such a reductive activity is part of what makes it such a productive and a process that makes me feel a real tangible sense of progress. Because if we finish another one of those complete, sub-trees of behavior, then I'll know I've only got these 2 left. And once you get about halfway down any tree, you really can see an end in sight and know you only have a couple leaf nodes to do. So that was our first layer. You saw a little bit of stuff with Makito. I'm going to make a commit at this point. And then in our next video, start tackling the next layer, which is probably going to be what to do with that time limit and how to replace a world at the individual cellular level. Should be fun. Thanks.